Yes, hi everyone. Hi Vic. Thanks for having me. So I will be talking about algorithmic interpolation approaches, which means I'll be excluding machine learning based approaches, except for a very quick comparison at the end of the talk. And if you don't know what HRTFs are, don't be afraid, I will catch you up to speed. So if you're listening through headphones, most likely what you're used to is that the sound sources appear inside your head and they will follow your movements. As opposed to what we want to achieve in virtual reality, which is being able to place sound sources everywhere in the three-dimensional space surrounding the listener, and for the scene to maintain stable as the listeners move. So this essentially means we're simulating spatial hearing, and in that case it's a good idea to understand how it works. So imagine you're sitting by the shore of a lake and someone is asking you to give the position of the dolphin, but also telling you don't look on the lake, just observe the motions of these two membranes here. This sounds sort of complicated, but this is actually what our auditory system is doing when analyzing the three-dimensional acoustic surrounding. Of course, with the difference, we're not observing waves in water, we're observing the sound pressure waves arriving at our eardrums, which is why these two membranes are here. So this means that all the spatial cues that we require for hearing or for spatial hearing are contained in these sound pressure signals arriving at the ears, which, luckily us being acousticians, we can measure them. We would measure them in a more abstract way by means of impulse responses, and we call them head-related impulse responses. Now what you see here is an impulse response for a source to the left of the listener. The blue line is the left ear signal, the red line the right ear signal. And you will notice that due to the spatial separation of our ears, there are so-called interoral time differences between the signals, so differences between the timing of the ears. And due to the acoustic shadowing of the head, there are also interoral level differences. Now these are the two main cues that allow us to localize sources in the horizontal plane, so in the left-right direction. If we then take the head-related impulse response and Fourier transform it, we arrive at the head-related transfer function. And here you see that the magnitude spectrum of those transfer functions looks quite delicate, which we take to our advantage and extract what we call spatial cues from those transfer functions. And those are the cues that allow us to localize sources in the medium plane, so vertical or up-down direction. So if all of the cues are contained in these signals and we can measure them, we can actually arrive at a very simple means of producing 3D audio, which is taking a dry source signal, convolving it with a pair of HRTFs, and then delivering those signals channel by channel to a headphone, which then, as indicated, should give the listener the impression of a drum set playing, for example, outside the head. Now this is only a very simple means of doing it. There's more complicated means, but basically if you're doing it with headphones, in every case you're needing HRTFs. So if it is so simple, then why should we interpolate? One possible answer to this is, in virtual reality, we usually want the listeners to be able to move. And if they move, that means that they would trigger lots of HRTFs for different head-to-source orientations. And we usually don't have HRTFs in the resolution required for someone moving in real time through in virtual or augmented reality. So the solution here is to start with a sparse data set, which is what we are focusing on. As you can see here, HRTFs are usually measured on a spherical surface. So each red point here denotes a source position for which we have an HRTF available. And we want to interpolate it, or also call it spatially upsampling, to a more dense sampling grid, which we can use for virtual reality. And the goal we have is to find an algorithm where we can take as little source positions in our sparse grid and arrive at interpolation results where the interpolation errors are, in the best case, inaudible. The problem is, if you look, for example, for head-related impulse responses in the horizontal plane, going from the left to the front, you see that the arrival time in these impulse responses changes, which makes them somewhat tricky to interpolate. And if you're looking at the source changing its elevation, coming down towards the center, you see that the magnitude responses change quite drastically, which also makes those transfer functions sort of tricky to interpolate. So I'd say for the past maybe 5 to 7 years, the de facto standard has been so-called time-aligned interpolation. So these two HRIRs, head-related impulse responses, are part of our sparse data set. And in the first step, we time-align those impulse responses by removing the linear phase component. And we will look into details later. This is just the rough thing how it works. We then interpolate by some sort of weighted superposition. And in the final step, reverse the time alignment by reconstructing the linear phase components. And this works pretty good for lots of source positions. In some cases, however, we are left with larger interpolation errors. And to improve this, we recently suggested what we call magnitude compensated and time-aligned interpolation. You can see that it has time-aligned interpolation as one branch, but we're introducing a parallel branch with the aim to design a correction filter to correct errors in the HRTFs after the time-aligned interpolation. And this is the idea behind it. So we are starting with an HRTF in the sparse data set. L stands for left, R for right ear signal. And what you see is the dark blue line, that's the input HRTF. And in the first step, we're applying some auditory smoothing to it, arriving at the lighter blue line. Now, there are two important ideas behind it. The first is, in case time-aligned interpolation doesn't work well, the remaining error is mainly a magnitude error, or what we would perceive as coloration, and we are analyzing coloration on a more or less auditorily smoothed HRTF that might look something like this. And then the second idea is that due to the smoothing, we are simplifying these transfer functions. And because they're simpler, they are easier to interpolate. And we make use of this in the next step, because we take our smoothed HRTF that we saw here and interpolate it to the desired source position. This will give us the light blue line right here. And we also take the HRTF after time-aligned interpolation, which is given in gray, and smooth it as well. And we arrive at the somewhat darker blue transfer functions. Now, because the smoothing is a nonlinear process, the order in which we apply these operations matters, and that is why we see differences between these two smoothed versions here. And because we think it's easier to interpolate the version that has been smoothed first, we can now, from these differences here, derive a correction filter by simply taking the difference between these two versions. So in this case, the correction filters look like this. We can see that for the left ear, the correction filter doesn't do much. So it seems that this was a source position where time-aligned interpolation worked well. For the right ear, the correction filter has gains of up to -12 dB. So we assume that this is a source position where time-aligned interpolation alone resulted in larger errors. And we then apply the correction filter to the HRTF coming from time-aligned interpolation. And let's see how that turned out. So in this case, we know the HRTF that is the true HRTF. It's given in dark blue here. And the gray lines show you the HRTFs after time-aligned interpolation. We see that for the left ear, that worked pretty well. But for the right ear, the time-aligned interpolation resulted in larger errors. And the magnitude compensation applied to it gives the sort of purplish lines. And we see that at least for this case, the interpolation errors have been reduced quite drastically. So that is the general theme. Let's go into some details. And I want to start with looking at methods on how to interpolate. And I want to introduce two methods that are used recently or often. The first one is called natural neighbor interpolation. So imagine you measured HRTFs at the position given by these points. Natural neighbor interpolation then takes your space and does a so-called Voronoi diagram. And as you can see, this diagram groups the space into polygons. But those are not any polygons. They have a very nice property. So if, for example, all these points contained in this polygon are closer to point 14 than to any other point. And in the next step, we are inserting our query point. So this is the point for which we want to interpolate an HRTF. And we recompute the Voronoi diagram. And the reason is that in the last step, we take the query polygon over to our original presentation, we overlay it, and then we can simply compute interpolation weights by calculating the overlapping areas here. So these are the areas AI here. If we normalize them to the overall area of the polygon, we get interpolation weights. And then the interpolation itself can be written as a simple matrix multiplication. So we can obtain our HRTF at the desired source position, at the query position, written as a vector containing the frequencies or time bands by a multiplication of a vector containing the interpolation weights and the matrix containing the HRTFs at the corresponding source positions. This is simple yet powerful. It has some very nice properties. The weights are smoothly changing because they are generated by the geometry and they are within a range of 1 and 0. We naturally preserve HRTFs at the sampling position. So if we tell our algorithm interpolate to exactly that position, we just obtain the HRTF we measured. And it works with irregular sampling grids in 2 and 3 dimensions. So overall, it is numerically stable due to the weights being between 1 and 0 and being smoothly changing over space. And it also does not overshoot, by which I mean the HRTF that we interpolated, all the values contained in it are within the range of the measured data. So going to the second interpolation approach, and I will try to perform the stunt to explain this on one slide. Let's see how it worked or will work. The second approach is called spherical harmonics interpolation. And in this case, we start with applying the so-called spherical Fourier transform to the data. And the way I've written it down, we are doing one spherical Fourier transform for each frequency. And for each frequency, we are considering all HRTF data on the entire sphere. So these two angles here give you the angles on a spherical coordinate system. Don't be scared. The way I think of it is that's basically a two-dimensional Fourier transform. And you can see the difference if you step back. We're basically integrating the product of our input data and basis functions. But the basis functions, because it's two-dimensional and spherical, are in this term spherical basis functions. I've shown you some of them here, whereby the radius of these balloon plots denotes the absolute value of these functions. So you can see for these functions, it's just a constant value regardless of the angle. And the red color tells you it's a positive value. The blue color tells you it's a negative value. Now these are just a few, there are infinitely many, and you can see they depend on the so-called order n, and with increasing order they get increasingly complex, and they also depend on the degree m, but we don't care too much why. And after we've applied the spherical Fourier transform, we arrive at the spherical harmonic spectrum. And let's think of it for now as a functional representation of our HRTF. Why functional? Because these basis functions here are analytical functions. We can evaluate them for any position on the sphere. And we're making use of that idea to obtain the interpolated HRTF. And we do that by taking the inverse spherical Fourier transform and we're evaluating it at the desired source position. So in this case, given by theta prime and phi prime. And you can see that we do that by a weighted superposition. So we're summing all the data we have. We superimpose the basis function and we weight with our spectrum. And that gives us the HRTF at that position. Now for simplicity, I was showing the integral equation here. If we have a discrete set of measured source positions, we need to use a discrete transform. But we can do that by setting up a matrix that contains the spherical harmonics for all orders n and degrees n, and for all positions for which we have measured HRTFs. And we can then invert these matrices using the pseudo-inverse, for example, to obtain our spectrum. Now, the very nice property of this is we can do a physically correct interpolation, however, only if we had very many HRTFs measured. So, sorry, not this time, I guess. And in this case, it's a bit more complicated because the transform may become numerically unstable depending on the source positions we have measured. And the result we obtain after the inverse transform can be overshooting. So we can have very large or very small values in the output outside the range of values in our measured data. So we have to be careful here. Why are we doing it anyhow? Spherical harmonics gained popularity, I'd say, due to ambisonics, which is a very widespread format for 3D audio reproduction. And they're also used in beamforming, so in microphone array processing. So we know how to interpolate. I'll take another zip. And then we're looking at how to align head-related impulse responses. So for the alignment, the first thing we need to do is estimate the linear phase component, or the delay of the HRAR, of the head-related impulse responses, which I'm just more or less showing arbitrarily by these lines here. Those are the points we want to estimate. We could do a very simple onset detection, which would mean we start at the beginning of the impulse response and, for example, search for the first sample that is less than 20 dB below the maximum of the impulse response. This is simple, yet it works often very well. We could use cross-correlation, which would mean we shift the yellow HRTF and try to find the shift value that maximizes the cross-correlation. And then this gives us the relative delay, which we, of course, can also use to align these transfer functions. There are also analytical methods. We could approximate the head as an open sphere and have an analytical solution for the delay. As you see here, this might not always be physically very plausible because sound doesn't travel through our head, except when grandparents talk to us. But we could also use a rigid sphere model, in which case we would account for diffraction, which is nice because it is more realistic. And because diffraction is frequency dependent, we would arrive at frequency dependent filters or delay estimates as well. In the next step, we would do the alignment, and in all cases you can think of this simply as a spectral division of the HRTF by a transfer function representing the inverse delay. Now, if we're using spherical head models, these transfer functions are directly obtained from the model. If we are estimating only the delays, we have to design these transfer functions, but that can be done, for example, as fractional delay filters. We then interpolate, for example, using natural neighbor or spherical harmonics interpolation. And in the last step, undo the alignment, and we can think of this as a spectral multiplication of the interpolated HRTFs with the delay transfer function evaluated at the source position we are interpolating to. So this means we know what HRTFs are, we know why we should interpolate and how we interpolate. Now it gets interesting. How does it perform in detail? And I want to start with looking at the effect of time alignment. So in black, I'm showing you an HRTF, a reference HRTF, which we want to interpolate. And this is an HRTF outside the head-shadow region. So it means that the connection between the source and the ear is not disturbed by the head, or is disturbed only slightly. You can see if we don't apply alignment, and in this case we're using only 6 HRTFs in our sparse data set, we make rather large errors at some places. And if we do the alignment, in this case we're looking at analytical open sphere and rigid sphere alignment methods, we already pretty drastically decrease the interpolation error or increase the quality of the interpolation. And what we also see, if we increase the numbers of HRTFs in the sparse data set, the interpolation quality more or less increases monotonously for all cases. Now this is a case where time-aligned interpolation works good, so outside the head-shadow zone. If we go inside the head-shadow zone, which means the direct line between the source and the ear is obstructed by our head, things get a bit messy in this case. So at first, we see interpolation errors are generally larger. But we also see there's no clear winner here. They're larger for all methods, and they don't really seem to systematically decrease as we increase the number of source positions in our sparse data set. Now, this is a bit of a specificality because we're using spherical harmonics interpolation. It would look different for a natural neighbor, but still interpolation errors would be larger in the head-shadow region. We then did a listening test to find out how many HRTFs we need for interpolation errors to be inaudible. And in this case, we are using speech or music-like signals, which we often term to be like real-life signals, so more relevant for practical applications. And in this case, we see if we're not using time alignment, we need approximately 170 HRTF, and we need only half as many if we do the time alignment, which is a nice outcome. However, inside the head-shadow region, we see first we need way more HRTFs, like by a factor of 4 or 5, and the time alignment doesn't give us the same improvement. And this fact was why we thought of introducing magnitude-compensated interpolation. What you see now are magnitude differences, so interpolation errors between the interpolated HRTF and the reference, but they are averaged across 96 HRTF sets of different subjects that we were investigating in this time. And they're shown over frequency. What we already know, if we do time-aligned interpolation, so no magnitude correction, and if we are outside the head-shadow zone, the interpolation errors are reasonably low, in this case using 26 HRTFs in the sparse data set. Now inside the head-shadow zone, interpolation errors increase in this case by a factor of 2 or a little more, which we've seen on the previous slides as well. Now, if we're doing magnitude compensation, we see that we are able to reduce the interpolation errors in the head-shadow zone almost to the degree of the outside the head-shadow zone, which is quite a nice outcome. And as a side effect, because we're doing this magnitude compensation separately for the left and right ear, we are also reducing the errors in the interaural level difference, so in this localization queue for the horizontal plane. And because we did this for HRTF sets of 96 different subjects, we can also tell that the interpolation works reasonably well for different subjects. We again did a listening test to find out more about the perceptual benefits of it, and we compared interpolated HRTFs to a reference HRTF. We did it for 2 source positions. These results are average across source position. And because we're directly comparing to the reference, a rating of 0 always means subjects did not perceive a difference. So first of all, we can see that subjects perceive differences, but we were using very little HRTFs in the sparse data set, so between 6 and 26. But we also see if using magnitude compensation, there is a significant perceptual improvement for the overall difference if using 14 or 26 sources. We observe the same if we ask the subjects to rate the coloration. We also see improvements in the perceived source position. In this case, however, only if we're using 26 HRTFs. And what I also find nice, we have less spatial disintegration if using magnitude compensation. To frame it in another word, the interpolated sources are spatially more compact if we're using magnitude compensation. So this means that if we don't apply it, for some cases you hear parts of the source at one position and, for example, a high frequency part at another position. And this is getting better if we are applying magnitude compensation. Now lastly, let's have a look at the effect of the interpolation kernel. Now the magnitude differences are also averaged across source position and frequency. And I'm showing you the results independent of the numbers of HRTFs in the sparse data set. If we're using only time-aligned interpolation, so no magnitude compensation, this shows us what we already know. Outside the head shadow zone, we have low errors. The errors more or less decrease monotonically. That's more or less, maybe that can be a true statement. And they are small. Inside the head shadow zone, we see that in this case, especially when we're using only a few numbers of HRTFs for the interpolation, spherical harmonics interpolation performs worse. And this is due to the numerical issues that we were seeing before. And we also see that different alignment approaches perform somewhat differently with differences between 1 to more than 2 dB, both between the alignment approaches and between the interpolation approaches. So if we then apply magnitude compensation, we see that errors for sources outside the head shadow zone more or less remain the same because time-aligned interpolation already works well there. But inside the head shadow zone, the errors are reduced. And what's nice, they are now almost independent of the interpolation and alignment approach. So all these lines are very close to each other whereby they were spread before. So it's been a lot of time me talking. If you didn't remember anything or everything, this is what I think is most important. If we're using time-aligned interpolation, we can reduce interpolation errors outside the head shadow zone. Inside the head shadow zone, larger interpolation errors may remain. If we're using or adding magnitude compensation to the equation, we can further reduce these errors inside the head shadow zone. And we do it in a way that errors are almost the same regardless of the interpolation and alignment approach, which is nice because we can now sort of choose either our favorite approaches or approaches that are matching the application we have in mind. And as a consequence, I said, we can basically combine magnitude compensation with any approach. Now the promised comparison to machine learning algorithms, short, but it's there. We've looked at 3 recent publications using learning algorithms for this. We were either comparable in the case when using very little HRTFs. If using some more HRTFs, we always outperformed them. But we were only looking at a very simple error measure, a technical error measure called the log spectral difference, where you compare differences between spectra. But in this case, on average, we outperformed these algorithms up to 2 dB. So what could be done next? We could think about directly including the ILD as a design constraint for the compensation filter. That might improve the perception of source position at lower, for sparse HRTF sets containing less HRTFs. It would somewhat decrease the coloration error maybe, so it would be a trade-off doing that. We are yet to do a listening test to find out how many HRTFs we need for the interpolation errors to remain inaudible. And we could consider combining this with learning-based approaches, because at some point, I'm pretty sure we're like drowning with waving flags to machine learning in this field as well. So if you want to try that yourself, Johannes Arendt, my co-author, or I was his co-author on other papers, published a MATLAB toolbox that can do all these tricks. We have from our latest study some audio examples published if you want to listen, and somewhat selfish and off-topic advertisement. We're currently developing Python toolboxes with the aim to help general purpose acoustic signal processing, and you can check those out as well if you'd like. So thanks for your attention.